But again, I just prefer to graph y1 equals y2, left side equals right side, find the points of intersection, and you're done. Does anybody have any questions you would like me to go over from this practice problem set?
5C.
Sorry?
5C.
5C? Certainly. So we want to determine an approximate solution. The fact, Jonathan, that this says an approximate solution tells me that if we were to solve this algebraically, we'd probably have to use the quadratic formula. So my question to you is, do you want to solve this algebraically? And I'm not trying to dissuade you. Or do you want to solve it graphically?
Algebraically, because I solved it graphically by this code. I just tried algebraically by trying to figure this out.
Okay. And I just want to make sure when you solved it graphically, you got the answer.
Yes.
Okay. So let's solve this one algebraically. You said C, correct?
Yes.
Okay. So we have 2 divided by x is equal to 3. I'm leaving a little bit of air between the terms here because I'm going to have to multiply everything in this equation by whatever I need to get rid of those denominators. And regardless of whether you might be expected to do this algebraically or not, it's a good mental exercise to keep your math skills in shape. You know, we could take the approach that probably your Math 20-1 teacher took, which is to say, what's the lowest common denominator and multiply both sides by it. I take maybe a little more pragmatic approach. I just say to myself, what is it I need to multiply everything by to get rid of this denominator of x? And the answer is x. And what is it I need to multiply everything by to get rid of this denominator of x minus 2? Well, that would be x minus 2. And my motivation here is that I want an equation that doesn't have denominators. Now, we might want to make a mental note here at this point in time that x is not allowed to be 0 and x is not allowed to be 2, right? Just in case we get to the end of our journey and we see x equals 2 as an answer, we would kick it out. It's not valid. What happens here, Jonathan, is these cancel. What happens on this side is the x minus 2's cancel, but everything else survives. So we're left with 2 times x minus 2 is equal to 3x times x minus 2. This is going to be where the quadratic nature of this equation makes its appearance. And then over here, oh, we also have more x squareds. We have 7x squared, 7x times x. It's kind of common here when you have things that cancel that you maybe miss pieces because visually it's a little bit cluttered. So we'll just double check. The x's are gone, 2 times x minus 2, 3 times x minus 2, 7 times x, it looks good. So I'm going to expand this out and have 2x minus 4 is equal to 3x times x is 3x squared, 3x times negative 2 is negative 6x, and then we have negative 7x squared. We're okay with that step? Okay. I'm going to simplify the x squareds. If I were working on my own, I might simplify it and move it over at the same time, but you know by watching me do math and by doing math yourself that it's so easy to make a mistake, right? If you try to cut corners. 3x squared minus 7x squared is negative 4x squared, and then we have our minus 6x. Now I'm going to move stuff over. So I move the 4x squared to the left side. It becomes positive. I have to add 6x to both sides. So I already have 2x over there. When I add the 6x, I'm going to get 8x. And then I have minus 4, and this is equal to 0. Does that look okay? Did you get to that point?
The point where I messed up that I see when going over it is I put down minus 4x instead of
Okay. And you know, that's That's the problem at this level, right? You make that little kind of mistake that really is just a numerical error, and it throws everything off. I notice here, we'll finish this off or go a little bit further. I notice that all of the terms in the quadratic equation are even. So I can factor a 2 out. Not that it really matters, but I'm going to speak to my calculus students right now. Don't get in the habit of dividing everything by 2. It creates problems when it comes to derivatives. Okay. We could, however, Jonathan, divide both sides of this by 2 because the right-hand side is equal to 0. Anyway, this is what we're trying to solve. So we have a equals 2, b equals 4, c equals negative 2. If we calculate b squared minus 4ac, just for kicks and to find out if this thing is factorable, we would have 4 squared minus 4 times a, which is 2, times c, which is negative 2. This becomes positive 16. This is 16. It's 32. It's positive because the negative times the negative gives you a positive. 16 and 16 is 32. So it's not factorable. Your solutions are going to be negative b, negative 4, plus or minus the square root of that thing, all over 2a, which would be 4. And that would give you your solutions. By the way, I made a point at the beginning of saying that x could not be equal to, it's just in red on the left there, x could not be equal to 0 or 2. Those are both rational, non-permissible values. The solutions we're getting for the equation are irrational numbers, so they're allowed because they're not the non-permissible values. Is that okay? Okay. Shazmaida. Could I have factored a 4 out? Look at that, I could have, yes. Thank you for that. My brain typically goes to the, oh, they're all even, let's take the 2 out. I didn't even consider 4. Definitely. You could have factored a 4 out, had 1x squared plus 2x minus 1. What you would have got for, might as well just do this, what you would have got for b squared minus 4ac is, I believe, 8. You would have got x equals negative 1 plus or minus root 8 all over 1. No, all over 2, I think. This might have been 2 as well. Yeah. Other questions? Ian? 4D. Okay. So use a graphical method and then use another method to, now we want to be careful here. It says, when it says use another method to verify the solution, I mean, we could solve it algebraically, but verification could be something as simple as taking your answers and putting them back into the original equation. But you said C? D. Okay. So what you're going to have to do here, let me rewrite it. Again, when I'm doing this algebraically, I'm leaving some space by each term because I know I'm going to have to multiply everything by something. And I'm trying to decide whether I should do anything with the 7 minus 5x. You should recognize that 7 minus 5x is the negative of 5x minus 7. So I think I will do something with that 7 minus 5x right now. I'm going to factor a negative 1 out of it. I'm going to do this over here. If I had 7 minus 5x and I factor a negative 1 out of it to reveal that there's a 5x minus 7 inside of it, the 7 becomes negative 7. The 5x, which is negative, becomes positive 5x. So these two things, Ian, are the same. Okay. So I can put, instead of 7 minus 5x, I can put 5x minus 7, and I can put that negative wherever I like. Not wherever. There's certain rules I have to follow. I can't put it on the other side of the equation. But I don't want to leave it in the denominator. And the reason is, if I leave it in the denominator, then you might be led to believe that I'm going to have to multiply everything by -1 to get rid of that. And when I have a negative as a factor in a denominator, I can put it wherever I like in that fraction. I could put it in front of the whole fraction. I would prefer to do this, though. Okay? So now what I'm going to do is multiply each term by 5x minus 7. And again, I'm going to go under the assumption here, Ian, that you can solve this graphically. You're asking about the algebraic approach. Okay, good. And this is 5x minus 7. And this is 5x minus 7. I'm multiplying everything by that offending factor. It's offensive because it's in the denominator, and we don't like that. And that cancels. So what do we have left? In the first term, we have a 3. Then we have plus, I might as well go ahead and multiply this through now, 5x squared minus 7x. Then I have plus, well, 5x minus 7. Oh, thank you. Equals. Then I have the positive 5x minus 7. And then I have that negative of the x squared minus 4x. I'm going to do with the negative the same thing that I did with the x on the other side. I'm going to multiply it through, giving me negative x squared plus 4x. And now I can solve this equation, or I can, take a step closer to solving it. I'm going to zero the equation by moving everything to the left-hand side. I have 5x squared on the left, and I have a negative x squared on the right. So when I add x squared to both sides, that will give me 6x squared. What about my x's? I have 9x here. I'm going to subtract it to the other side where it will join forces with the negative 7. What's 9 and 7? Negative 16x. I have a 3 on the left, but I need to add that 7 from the right to get this. So I'll step back and look at that. I have 6x squared. I have 9x, negative 9x, negative 16x. I have 3 plus 7 is 10. You're okay to that point? Okay. We can factor out a common factor of 2 and have 3x squared minus 8x plus 5. 3 times 2 is 6. 3 times negative 8 is negative 16. 3 times 5 is 10. Let's do a b squared minus 4ac calculation. That would be negative 8 squared minus 4 times 3 times 5, which gives me 4. But I don't, maybe somebody out there can double check that. Getting the thumbs up. I'm getting 4, which is a perfect square. Some people might just prefer to keep going with the quadratic formula. I'm not that kind of person. I would rather factor it. Let's see. It's going to be 3x and x. It's got to be 5 and 1. Thinking if I put the 5 here and the 1 here, that gives me negative 3x for the outer product and negative 5x for the inner product, which is negative 8x, which is what I want. That means that 3x minus 5 equals 0. That means that x minus 1 equals 0. So solving this little equation for x gives x equals 5/3. This one is x equals 1. One final thing we should do, go look at the original equation. The non-permissible values or value would have been a statement that says x is not equal to 7/5 because we can't divide by 0. And that's fine then, because the two answers we got, neither of them are 7/5. Is that okay?
Would it also be negative 7/5 as well?
No. The reason is you're looking at the 7 minus 5x. Is that what you're doing? When you say would it also be negative?
Well, I was looking at, because there's both sides, and one, we factored out a -1.
Right. So you have a factor. This is what you have on the other side.
Yes.
That's still going to be a non-permissible value of 7/5.
How come when we figure out the non-permissible value, we don't figure it out from like the actual how it was written down in the textbook and say that it can't be?
Well, we do. We do. Let me address that. First of all, if you go with the original expression in the textbook, it's this, which is what I wrote here, which is what I thought you were talking about. Then you mentioned this. But let's go back to what's in the original equation. This is a denominator, correct? And that means that that denominator cannot equal 0. Solve that for x for me. Did you just say ah? Okay, so you get it, right? If you look here, and I would dissuade you from looking here because I want to impress on you the importance of going to the original equation, but you could look here. This -1 plays no role in non-permissible values. It's a factor of -1. What's important is this is not allowed to be 0 because it contains the x's. So you're going to end up with the same non-permissible value. You're good now? Okay. We're going to move on now to lesson 10.1. By my count, we do 10.1 today, 10.2 tomorrow, 10.3 Wednesday and Thursday. That would mean Tuesday and Wednesday of the following week. When we return, we're reviewing for those 2 days. And that would mean your unit exam for this unit, which is chapter 9 and 10, your unit exam will be Thursday of next week. So this is section 10.1. The lesson deals with sums and differences of functions. The ultimate goal here is for you to understand the relationship between two functions and what we call the sum of the two functions and understand what it means. We also have to deal with some notation, which seems a little weird that they come up with new notation for something that you might think is not really needed. But we got to deal with it. So we're also going to be talking about domain and range of a function that is the sum or the difference of two functions. And I hope you understand, but just in case, the word sum means the result of addition. The word difference means the result of subtraction. And before we get started, I want you to give some thought to this question. When you find a sum, does it matter the order in which you add the items? The answer is clearly no. When you find a difference, does it matter the order in which you subtract the items? Absolutely. Of course it does. Because 10 minus 3 is 7, but 3 minus 10 is not 7, it's -7. So we start off with some, and write equations of functions that are sums and differences. We start off with some definitions which are fairly obvious. When you talk about the sum of two functions, we write, and listen to how I say it, we write f plus g of x. That's how you should think of that in your head. If you were to say it out loud, it would come out as f plus g of x. What it means is f of x plus g of x. So it's not some kind of great mystery. And by the way, this isn't equal to f of x plus g of x because you're somehow multiplying the x through. This is not a variable f plus a variable g. It means two functions being added. The difference of two functions can be written as f minus g of x. And if you don't like that pause, then you should really think of it as f minus g quantity of x. The whole thing is a function of x, and it means f of x minus g of x. So as a first example here, I'm giving you two functions, f of x equals 2x plus 1, g of x equals x squared. These two functions by themselves are very basic functions. A linear function from grade 10, the most basic quadratic function from grade 11. Determine the equation of h of x if h of x equals f plus g, quantity of x. Well, all that means is h of x equals f of x plus g of x. If we look up at the top of the screen here, f of x is 2x plus 1 plus g of x is x squared. We now have h of x that consists of three terms. None of those three terms are similar, so we can't really simplify it, but we would probably write this in kind of a standard form where we put the highest degree first, then the next highest degree followed by the constant term. And as far as exam questions go, this is not worthy of being on an exam. This is just warming you up to what it means to say the sum of functions. And now what we want to do is graph these, but we're going to graph these by making a table of values. There's a value in doing this in terms of your understanding what I think is the most important point about today's lesson. So we're leading up to something. So if I put -2 in for x, I would have, and my goodness, I'm not going to write out the substitution for all 15 of these blanks. I'm going to get -2 times 2 plus 1, which I believe is -3, but I want you working along beside me, figuratively speaking, and double checking my arithmetic. Okay. When I use -1, I get -1. Now I'm going to cheat a little bit here. I know that the slope of this line, if I were to graph it, is 2. So every time x goes up by 1, y goes up by 2. So this would be 1, this would be 3, and this would be 5. But you can double check with substitution. Am I okay with that? Are you okay with that? Okay. So now we go x squared. Oh, this is like stealing candy from a baby. I square x, I get 4, 1, 0, 1, and 4. Of course, shouldn't really need to remind you, but when you square a negative, it becomes positive. Now, what I would like you to do, I would like everybody right now to calculate what number we put in for h of x when x is -2. Would I be correct in saying you got 1? Okay. I'm going to fill in the rest of the table, and I want you to watch me filling it in. And I want somebody to explain to me how I was able to fill that in so quick. Jonathan?
Because h of x is the sum of x squared and 2x plus 1. So if that means that's the sum, then if you take just the sum of both answers, so the first one would be -3 plus 4, you get 1.
Right. This is 2x plus 1, also known as f of x. Right? This is x squared, also known as g of x. This is h of x, which is the sum of f of x and g of x. It's 2x plus 1, which is the first column that we filled in, plus x squared. And now I can really tell you this big thing that is the most important thing is that when you try to find the sum of two functions, you add the y coordinates. So when we look at an x coordinate of -2, an x coordinate of -2 gives a y coordinate on f and it gives a y coordinate on g. The y coordinate on h will be the sum of those two y coordinates. There's a slightly different way we could approach this. I've never seen this as mapping. I would have to believe that if you put it on a diploma exam written response, I think whoever marked it would go, yeah, I get your intent here. I understand what you mean. When you have f of x plus g of x, the mapping to give you h of x is that the x coordinate comma y coordinate on f and the x coordinate y coordinate on g map together to give you an x coordinate, and the y coordinate on h will be y of f plus y of g. So this represents a point on h, this represents a point on f, and this represents a point on g. It's the y coordinates that we're playing around with here. Okay, so now we'll plot these points. I've got the numbers up here. -2, -3 is a point on f, and then -1, -1. You want to be very careful in interpreting this table that you've created. These are the ordered pairs I'm using for f. This will be the ordered pair I'm using for g. It's kind of a little cluttered or confusing. So then 0, 1. And I'm going to tell you right now, I do not want you connecting the dots. This is not the point. Okay? And then 1, 3. Of course, you go over 1 and up 2 every time. So that is f of x. And I'm just going to put the letter f down here. Now, what about g of x? Well, g of x is -2, 4. -1, 1. 0, 0. 1, 1. 2, 4. If you want, you can certainly draw these, but that's, again, not my intention here. That's g. So what I'm about to show you is what I've already told you here and what Jonathan already explained here. It's just that I'm showing it to you in a visual way now. When you take a look at when x, this is not an asymptote, I'm just putting a line here so I can talk about when x is -2, the red point is the y coordinate on f, the green point is the y coordinate on g. So the point on h is the sum of this number and this number. And I plotted those 2 points in the wrong place, didn't I? They should be up one more at 4. So it's the sum of those two numbers. You're looking at a specific x coordinate, and then you're looking at the two y coordinates and you're adding them. So 4 plus 3, -3, is 1. So this is where h of x is going to be. Then you can do the same thing. You can move over to move over to -1 and look at those two y coordinates. Those two y coordinates are 1 and -1. When you add them, you're going to get 0. And you just continue this process. And the reason why you have to be able to do this from a graph is sometimes you're not given the equations. Most of the times you're not given the equations. When I go over to x equals 0, so I'm looking here now, I'm going to add those two y coordinates to get 1. 0 for a y coordinate plus 1 gives you 1. And I just continue this process. Now I'm going to add 1 and 3 to get 4. I don't know if I'll be able to plot this one if I have enough room or not, but I'm going to add 4 and 5 to get 9, and I do. It's going to be there. I think we should draw h of x. I don't think we should just leave it as a series of dots. Of course, it goes up, and you could use some symmetry here to figure out that it goes through this point and this point. But whether you do that or not is up to you. I don't care. Again, what you want to recognize is you're adding y coordinates. Everything in this example, everything leads up to that conclusion. You add the y coordinates. That's why we did everything. What is the domain and range of h of x? Well, we can look at the graph and we can see the domain is any real number. X is any real number. The range happens to be y is greater than or equal to 0 because it's a parabola that opens up with its lowest point on the x-axis. Determine f of 4, g of 4, and h of 4. That's what this next question is asking you to do. So I'm actually going to show my work here. I don't think you really need to. F of 4 would be 2 times 4 plus 1. That gives me 9. G of 4 would be 4 squared. That gives me 16. So what will h of 4 be equal to? Well, we could put 4 in here and have 4 squared plus 2 times 4 plus 1. But again, and I realize that at times I can be overly repetitive, but I would rather be repetitive, hopefully not boringly so. I would rather be repetitive and you really get an idea. This gives us the 9. This gives us the 16. So h of 4 is going to be 9 plus 16. We don't actually have to go through the substitution here into h of x. So you're going to simply have 9 plus 16. Bottom line is h of 4 is equal to f of 4 plus g of 4. Which, I think this is really interesting because we've gone all the way around the block, and you know what I'm telling you? H of x is f of x plus g of x, which was the question, right? F, g, and h are functions. They're y values. So you add the y coordinates. How are the y coordinates of the points in the graph of h of x related to the y coordinates on f and g? For a given value of x, the y coordinate on f plus the y coordinate on g give you the y coordinate on h. Which is maybe, I think, at least the fourth time we've said that. It's the y coordinates that are involved here. All right, let's take a look at another one. Any questions with anything in example 1? Ian.
There's addition and subtraction rule. Is there a division?
Tomorrow. And it gets considerably more complicated. But I can tell you this, I mean, in anticipation of tomorrow's lesson, the product of two functions is going to be found by multiplying the y-coordinates. The quotient is going to be found by dividing the y-coordinates. It's all about the y-coordinates. It's just that when you multiply and divide, things get more complicated. All right, number 2, consider these two functions. Can you double check to make sure that those two functions are the same as the ones that I have up here compared to your note package? They are. So we have y equals root x minus 1, y equals x minus 2. I'm calling them f and g. What's the equation of f minus g of x? Well, that's the equation of f of x minus g of x. So it's probably pretty obvious, but when you write f minus g in this set of brackets, the letter that goes first is the function that you write first, then you subtract the second one. Well, if f of x is root x minus 1, then h of x is root x minus 1 minus g of x, which is x minus 2. What grievous error have I just made? Ian? Brackets. And it's the standard practice in high school math, and math in general, I suppose, that you simplify things. If you don't need the brackets, don't write them. Now, just a second, don't misinterpret what I'm saying. We need to write them here. But do we need to write them in our answer? No. What we can do is write this as h of x equals root x minus 1 minus x plus 2. So I can distribute that negative in here. And again, we're not graphing these on our calculator necessarily. I want to reinforce something here, which is why I want us to graph them using a table of values. Whoops. Not what I meant to have here. Give me a second. So when we fill this in, and I start off with f of x, and I put negative 2 in for x, then you're going to have the square root of negative 2 minus 1, which is the square root of negative 3, and you can't do that. I mean, we've already talked way back in chapter 2 that if you have root, and also in math 20, if you have this, then x minus 1 must be greater than or equal to 0, because you cannot take the square root of a negative, which means x has to be greater than or equal to 1. So we are unable to calculate a y-coordinate for these. When we finally get to 1, we can calculate the y-coordinate. 1 minus 1 is 0, root 0 is 0. 2 minus 1 is 1, root 1 is 1. I hope you can appreciate why I chose the next two x coordinates. 5 minus 1 is 4. The square root of 4 is 2. 10 minus 1 is 9. The square root of 9 is 3. And then we move on to the next column, x minus 2. So negative 2 minus 2 is negative 4. Negative 1 minus 2 is negative 3. 0 minus 2 is negative 2. 1 minus 2 is negative 1. 2 minus 2 is 0. We had a really nice pattern going here, but be careful because the pattern now is broken because we're going up by 1 for x, and then all of a sudden we go from x equals 2 to x equals 5. So be careful. 5 minus 2 is 3. 10 minus 2 is 8. Can we all agree on those first two columns? Okay. I don't think I need to do the substitution for the third one, because what this third column is it's taking x minus 1 and subtracting x minus 2. but x minus 1 is the column under f. X minus 2 is the column under g. So I just subtract them. Now this is very important. Now there's a little wrinkle here. What do I get when I subtract something that's undefined minus 4? The answer is I don't get anything because I can't do the subtraction. You can't do operations on numbers, on two numbers, unless the two numbers exist. So you can't subtract the two functions if there's a part where one of the functions isn't even there. So this is undefined then. This is undefined. This is undefined. Then I can go 0 minus negative 1, 1 minus 0, 2 minus 3, 9 minus 8. Did I write something down wrong here? Just a second here. 2 minus 3 is negative 1. That should be 3, shouldn't it? Not 9. Square root of 9. That should be a 3. Three minus 8 is negative 5. We good? Okay. So now we're going to plot the points. Well, you should actually know what root x minus 1 looks like. And don't draw this, but root x, you learned in chapter 2, starts here and looks like that. So root x minus 1 is that thing shifted 1 to the right. But if we plot the points, 1 comma 0. So I'm looking at this x coordinate and this y coordinate for the first function. 2 comma 1. 5 comma 2. 10 comma 3. That is f. And I don't care if you draw the curve or not. But I do care that you understand that this function f only exists from x equals 1 to the right. Okay? I'm going to write that down in a slightly different way in a minute. Now what we're going to do is graph, and I'll graph it in green, this ordered pair. Negative 2 comma negative 4. Then I go to negative 1 comma negative 3. Then I go to 0 comma negative 2. It's going to be a straight line, of course. Then 1 negative 1. 2 comma 0. Then we jump to 5 comma 3. And 10 comma 8. And again, you could take a ruler and draw that, but I really don't care. So let's take a look at plotting. We're going to use brown here. Let's take a look at plotting this point, which is at 1 comma 1. The x coordinate on h is 1 and the y coordinate is, 1 comma 1. So we're going to plot that point. But, and this is, it's not tricky. You just have 3 functions here and you have to follow them carefully. The y coordinate on h is found by taking the y coordinate on f minus the y coordinate on g. So the y coordinate on f is 0 minus negative 1, which gives you positive 1. Let's try that here. If I take the y coordinate on red at x equals 2, that's 1, and I subtract the y coordinate at x equals 2 rather. At x equals 2, the y coordinate on f is 1 minus, the y coordinate on g, which is 0. 1 minus 0 is still 1. If I go to the next one, the y coordinate on red, which is f, is 2, minus the y coordinate on g, which is 3. 2 minus 3 is negative 1, and if you look up here, there's the negative 1. So we can arrive at the negative 1, actually, everybody, in 3 ways. You could put the x coordinate into the function h. You could calculate f and g and subtract them, or you could just look at the graph and subtract the y coordinates. In either case, this ends up going down here at negative 1. If we go over here, the y coordinate on f is 3 minus 8 gives you negative 5. So this is what we end up with. In the past, I've chosen x coordinates between 1 and 2 to illustrate something, and then I've discovered that it really doesn't matter. Trust me, if we did that, the graph goes up a little bit and then down. So what this graph looks like is something like that. We can confirm that with a graphing calculator, by the way. Any questions with the data points or the graph? All right. What's the domain of h of x? So now comes something that's a little bit different. When you take a look at example 1, let's look at the graphs in example 1. That red graph, which I'm going to actually draw in now, that red graph went on forever in both directions. The domain was any real number. The green graph also had a domain of any real number. Since the brown graph, which was h of x, was the sum of the 2 other functions, if the 2 other functions existed everywhere, then you could add them together everywhere. And that's why the domain of the brown graph is any real number as well. But when you take a look now at these graphs, I'm going to put a number line up top just to make my point. You can draw this if you like. You can put it someplace else. It doesn't matter. The domain of the red graph is from here to the right. That's the domain of f. The green graph has a domain from negative infinity to infinity. There's a whole region over here where only one, there's a whole region over here where only one of the functions exists. So in that region, you can't subtract the 2 functions because one of them is not there. Which means that the domain of the brown graph has to be the domains overlap. Where the 2 domains overlap, that's going to be the domain where you're allowed to subtract them or add them. So, or we could just look at the graph and see that x is greater than or equal to 1. I really hesitate here in even including D in my notes. It's not important. Well, let's answer the question first. If I drew it properly, then I would say here that the range is y is less than or equal to about 1.2. You calculus people, you know that we could find the coordinates of that by taking the derivative and proceeding with a first derivative chart. So I'm going to say that y is approximately less than or equal to 1.2. The only reason I think I hold on to keeping this in here is the following. We have a rule for finding domain, and I'll talk about it specifically in a second. The domain is going to be the domain that's common to both. We have 0 rules for finding ranges. The only way you can ever find the range of a function in this chapter is to look at the graph. Ian?
But don't you still have to look at where they overlap?
Not for the range. Because if you take a look at where they overlap, the range of one of these functions is negative infinity to infinity. The range of the other one is greater than or equal to 0. So they overlap for y values greater than or equal to 0, but that's not the range of the new function. And you'll get caught into that trap of thinking, well, okay, if where they overlap horizontally is the domain of the new function, then shouldn't it be where they overlap vertically is the range? And the answer is no. The reason for it, and then we'll move on, is because we've set things up to define y as being the sum or difference of the numbers. We've set things up so that x is shared. We look at a single x coordinate and add or subtract the y's. We look at the next x coordinate and add or subtract the y's. So it's the x coordinates that define where we're allowed to do this. Okay. How are the y coordinates of the points related? The y coordinate on H can be found by taking the y coordinate on F minus the y coordinate on G. And I know I've said this, but I'll say it again. You can't subtract the other way. If you subtract the other way, you will not get the right function. What is the domain rule? We're going to deal with this tomorrow as well with products and quotients, but it will get a little more messy. Listen, if you're going to add or subtract y coordinates of two functions, you will only ever be able to do that where both functions exist. Horizontally where both functions exist. If you have a function that starts at the tip of my nose and goes to your left to negative infinity, and you have another function that's defined everywhere, you cannot add the two functions over here to the right of my nose because one of them isn't even there. So what the domain rule says is it's the domain common to both. If I told you, quick examples, here are two graphs, and you need to be careful because I'm going to, when I do A, I've got the two graphs on the right. So these two graphs that are on the right up here are at the top of your page, so be careful. There are two functions. By the way, speaking of domain rule, for F, would you agree that's the domain of F? Positive, rather. Would you agree that's the domain of F? Would you agree the domain of G is also that? Yeah? Well, then you can add them together, the y coordinates that is, any place in that domain because the domains are perfectly matching. So how are we going to graph F plus G? The answer is you are going to be looking at x equals 1, and you're going to take the y coordinate on each function and add those y coordinates together and plot the new point at x equals 1. So when x is 1, the y coordinate on F is 2, the y coordinate on G is 0, 2 plus 0 is 2, so at x equals 1, y is equal to 2. And then you move on. Then you move on to x equals 2. And you take the y coordinate of 3 and you add the y coordinate of 1 and you get a y coordinate at x equals 2. You get a y coordinate of 4. We do the same thing at x equals 3, we add the two y coordinates. So we're going to add 2 and 4 to get 6. Can somebody explain maybe why that part of our graph is going to be a straight line? Ian?
Because both are going up by the same slope.
Yeah, they're parallel lines, right? So when I take that y coordinate of 1 and I add it to the other one because the slopes are the same or they're parallel, you're going to be adding the same difference each time. It's going to be going up by the same amount each time. We can go on now to x equals 4, and we will be adding the y coordinate of, well, 4 plus the y coordinate of 1. 4 plus 1 is 5. And then we repeat it for the last possible point that we can use. 5 has an x coordinate of 5 gives y equals 4 on one and y equals 0 on the other one, which is 4. So this is what the graph looks like. And I'll just tell you right now, if I said to you, I didn't give you a grid, I said to you, what is the range of f plus g? This is what you would have to do to see what the range is. You cannot wrap your head around it. The range is 2 to 6. And there's no easy way to do that. Let's try f minus g. So we're going to take the y coordinate of 2 and subtract the y coordinate of 0. 2 minus 0 is 2. Then we move on to an x value of 2, and we look at the y coordinates at those x values of 2, and we're going to take 3 minus 1, which is 2. If we repeat for the next one, we will also get 2 because these lines are parallel. They have a vertical distance that's the same between each of them. One of these lines is exactly 2 above the other line. So when you subtract all those points, you get 2. Moving on now to x equals 4, which would be this point and this point. I'm going to take 4 minus 1, which is 3. And then the last point will be at x equals 5, where the y coordinate on the top function is 4 and the y coordinate on the bottom is 0. 4 minus 0 is 4. So this is what f minus g looks like. I'm going to ask one final question here just to get your brain pumping a little bit. What do you suppose g minus f would look like? Arden? It's a vertical reflection. Because let's face it, when you subtract two things and then you change the order in which you subtract them, you get the negative of what you got. So all of these y coordinates would be opposite. What g minus f would look like is that, roughly. I didn't do a brilliant job drawing it, but it would look like that. So a vertical reflection can be accomplished when you subtract functions by subtracting them in the opposite order. You have about 20 minutes here today to work on this practice problem set. Don't do 12 and 13. This is sums and differences. Tomorrow we will look at products and quotients, and then for the rest of the week we're going to be looking at something called composites of functions. So get started on that. I will be around to help you out shortly.